Assalamu alaikum everyone. So lecture number 19 and the topic is encoding techniques. So these are the main points which we will be talking about. First of all, data representation. So when we talk about data transmission, so we have to represent that data so that we will be able to transmit it from one point to another point. So there are different ways of data representation, and that data representation counts when we have to transmit data by using some channel from one point to another point. Then of course signaling, so we have to transmit that data which has been represented by using some technique, some technology. So in order to transmit that data via some channel, we will be actually using some sort of signaling. So what is signaling is, and how we are going to use different signaling techniques in order to transmit data from one point to another point. Then there are different encoding techniques. So we'll be talking about specifically focusing on we have digital data and we are going to use digital encoding, digital signaling you can say. And then of course that's digital data, digital signaling, and that is all about or something about line coding. And of course there are some certain advantages of digital data, digital transmission, for example because the data is native for VLSI, for some other circuitry, so it has its advantages as well as disadvantages if we are going to use digital data and digital signaling. And then we will be talking about the signal elements versus data elements. So in signals we are actually dealing with bauds, so how much data a signal can accommodate, right? And the data elements, we are talking about the bits and bytes. So here is data rate, that is about data elements, and then the signaling rate, that is all about baud rate. We also can name it pulse rate or modulation rate. Then there are different types of encoding. So we will be talking about different types. We will talk about unipolar encoding, where we are only using one level, and then polar encoding, and then biphase encoding. So polar encoding includes non-return 0 and then return to 0 encoding, and then biphase encoding, Manchester and differential Manchester, and bipolar encoding also, right? Biphase and bipolar and unipolar. Then after that we will be talking about the multi-rate 2B1Q and multi-rate AB6T, 4D PAM5, multi-transition MLT3, and block coding. So these are the topics which we will be going through one by one in today's lecture. So let's start after having some sort of introduction about data representation. So we are actually living in the analog world, right? So we need to store data, we need to transmit data. So there are different ways, different means, different technologies. So in that case, the data representation and the signaling techniques that we are going to use in order to transmit data by using some channel, by using some medium, is very important. So we can have data in two formats. First, analog, for example my voice, human voice, and we can convert that analog data into digital data, right? And then we can have another data type or data representation, that is digital data, that is our computer file, or the data that we normally store in our USB stick or maybe hard disk. And this is something about the data representation, right, or data storage. And for example, when we talk about the human voice, so we can use video tapes in order to audio tapes in order to record the analog voice. Then of course we store data and we use data, we access data, we retrieve data, so we have to store data, then maybe transmit data from one point to another point, and at some point in time we need to retrieve that data. So in order to transmit, we use some signaling techniques, and that signaling techniques is very important when we talk about the data communication. So transmitted signals representing the data can also be in two different types. We also have two different types of signaling, analog and digital. The conversion of digital data or user data into transmission signal is called encoding, right? So here are different techniques. Encoding techniques must be put in a format, right, signal suitable for the transmission media. So actually our goal is to use some media. It can be airspace, it can be guided media, it can be unguided media. There are a lot of different media, and we have already gone through the classification of different media depending upon their characteristics, right? So here are the encoding techniques. So we have four different choices over here. So first, if we have digital data, and digital data mean that the data representation, the representation of the raw data, right, by using digital mechanism. So if we have digital data, and we can use digital signaling as well in order to make this data compatible with the underlying transmission media which we are going to use. And then we have another choice, data is digital, so we can use analog signaling in order to transmit that data or compatible that data in order to make that data compatible with the channel. And then if we have the analog data, for example my voice, right, so we have again two choices. One is analog data, and we can use digital signaling, right? So we can use for example PCM in order to transmit that data from one point to another point, or to make it compatible for some media and so forth. And then again digital data, analog data and analog signaling. So we have four choices over here: digital data, digital signaling. So first part is, let me write down over here. So first part is, that is about data representation, and the second one, that one is about signaling. All right, okay. So here you can see we have, if we talk about digital data, right, so we have two choices. Here are the variation, and the first representation is the same, digital data, and we can use digital signaling as well as analog signaling. So if we talk about the analog data representation, so again we have two choices, digital signaling and analog signaling as well. So here are four possible cases, and this is somewhat same but more explanation, with some more explanation. Digital data, digital signal, and we have to use line encoding. It's less complex, right? Because if I'm going to transmit data from my computer to some other computer, right? So we know that the devices are very cheaper, the media is very cheaper again, and as a result we have less complexity, and the cost is again on the lower side. Whenever we have analog data and we have to use digital signaling, so we use A to D converter for example voice data. This is again the analog data, and video data as well. And if we have digital data and we are going to use analog signaling, so we are actually using digital modulation for optical fiber and unguided media. Digital data, and we are going to use analog signaling, right? So there is one example of fiber optics, And then another example of fiber optics and unguided media. Free space, you can say analog data and analog signals, so we use analog modulation to transmit baseband signal easily and with the lower cost. So here is the graphical representation or interpretation of the digital data, discrete continuous voltage pulses. So here is the data that we are going to represent by using digital signaling, right? So you can see this is 1, so 0 is high and this one is low, it is still low, 1, and then again 0 is high. If we talk about the length of this pulse, right, this level, so it's 0.02 millisecond, right? So, and this is the voltage, 5 volt, right? Okay. Signal element, binary data encoded into signal elements. So we are actually going to represent binary data by using digital signaling. So here are some of the advantages of digital transmission. So digital technology we have to use, so it's low cost because of VLSI technology, digital data integrity, longer distances over lower quality lines, so we can traverse long distances, and then capacity utilization, so the bandwidth is again available bandwidth is on the higher side, and they are economical as well. So high degree of multiplexing, easier with digital techniques. So we are a lot of different techniques that we can use in order to enhance the capacity of the underlying technology. And then security and privacy. So we have a lot of different encryption schemes and a lot of different mechanisms so that we can make the data secure. So as a result, we can attain or maintain a privacy. Integration, if we talk about the integration, so we can treat analog and digital data similarly. So it's very easy if we have analog on one side and we have digital on the other side, so integrity is again less complex. So here are some of the disadvantages and cons of the digital signaling. Greater attenuation, so you can see as the signal moves longer distances, right, or has to traverse longer distances, we have to face attenuation, right? So here is the example. So this is the voltage, or you can say the data transmitted from the transmitter side, and on the receiver side we are receiving this. So you can see the great amount of attenuation over here, right? So it's rather difficult for the receiver, right, to extract the data, right? So maybe there are some errors on the receiver side. So if we talk about digital to digital conversion, can represent digital data by using digital signals. There are 3 techniques that are involved that we can use: line coding, block coding, and scrambling, right? We always require line coding. Block coding and scrambling, it depends in which scenario or what technology we are going to use, what communication system we are going to use. So depending upon that system, block coding or scrambling may or may not be required accordingly. So let's talk about line coding. Encoding. So it's a process of converting the digital data to digital signals, and we assume that the data in the form of the text, numbers, graphical images, audio or video are stored in computer memory, right? So of course in our computer memory or computer hard disk, what normally we have files that include text or maybe images, and then we have maybe still images, graphical images, and maybe the audio stored digitally into our computer, and then the video, maybe moving images, right? So these are the different types of data that we can store in our computer. So we have to perform line coding in order to transmit that data from one point to another point. Line encoding and decoding. So here is the digital data encoder. You can see we are having encoder over here. So before launching it onto the transmission media, we have to perform line encoding, and here on the receiver side we have a decoder, and this data is decoded and sent received by the or extracted by the receiver. So let's talk about the signal element versus data element, right? So that is very important when we talk about the data communication. So our ultimate goal is to transmit maximum data from one point to into another point with minimum amount of time, right? So data rate, bits per second, megabit per second, so whatsoever you can take. Element is the smallest entity that can represent piece of information, and this fundamental unit we call it bit, binary digit. Digital data communication, signal element carries data elements, so these are the signals who are actually carrying data from one point to another point. A signal element is the shortest unit if we talk about the time span of a digital signal. Data elements are what we needed to send, right? So actually our goal, our objective is to send data. In order to do that, we are going to use some signals, right? So signal can have 1 bit, can accommodate 1 bit, maybe 2 bit, maybe more bits, number of bits, right? So that is what we have to talk about, that in how many baud, or in one baud, how many bits we can transmit, or on the receiver side, how many bits we can receive in a single baud. Need to send signal elements, right? And that what we can send data elements are being carried are the carriers. So signal elements are the carriers, and we have to send the data. So here ratio R, which is the number of data elements carried by each single element, right? So here in this figure we have several situations with different values of R, and that is the ratio. So here you can see we have 1 bit, right? And this is the span, and we are using one signal element in order to represent 1 bit. So it means bit rate and baud rate, they are the same over here. One data element per one signal. So R is equal to 1, ratio is 1 to 1, and here you can see one data element and we are using 2 signals, right? And here the ratio is 1 by 2. One data element, right? And we are using 2 signals, so ratio is 1 by 2. And over here the scenario is different, right? So you can see that we are using one signal element in order to transmit 2 bits. So this signal element, it can accommodate 2 bits, right? So whenever the receiver will receive this, so it will decode this as 0 1, and it will decode this as 1 1, and here again we have 1 1, right? So 2 data elements, 2 bits per one signal, so the ratio is 2 over 1, and you can simply say 2. And here we have another scenario, right? So we are using 4 data elements, right? And 3 signal elements over here, right? So 4 data elements per 3 signal elements, and the ratio becomes 4 by 3, right? So 4 data elements and 3 signal elements, 1, 2 and 3, so ratio is 4 by 3. So let's talk about now, after explanation, data rate versus signal rate, or baud rate, or maybe pulse rate, or modulation rate. Number of data elements, bits sent in 1 second, right? The unit is bit per second, BPS. The signal rate is the number of signal elements sent in 1 second, that is the baud rate, is baud. Data rate is sometimes called the bit rate, and the signal rate is sometimes called the pulse rate, modulation rate, or maybe the baud rate. So we have to take into account bit rate and baud rate, maybe modulation rate. So we need to take into account the relationship between data rate and signal rate, right? Bit rate and baud rate on the value of R, right? So depends on the data pattern C. If we have a data pattern of all ones or all zeros, it may be different from a data pattern of alternating zeros and ones, right? So here is the relationship S, right? C into N into 1 over R. R is the ratio. N is the data rate. C is the case factor, right? Worst, best, and average. And R is the ratio between data element and the signal rate. So here, let's have an example in order to understand this relationship. A signal over here is carrying data in which one data element is encoded as one signal element. So ratio is of course 1. If the bit rate is 100 kilobit per second, what is the average value of the baud rate if C is between 0 and 1? Right? So this is the problem we have to address. So here we have to assume that the average value of C is 1 by 2. Right? So because it's between 0 and 1, so if I have to take the average, so 0 plus 1, so we have two elements over here, right? So 1 by 2. The baud rate is then, right? So we have all the values. R we know 1, right? And we also have bit rate, right? So C into N into 1 over R. C is 1 by 2, and this N is 100 kilobit, so 100 multiplied by 100, or you can 100,000, or here we have ratio 1 over 1, right? Bit rate and baud rate, they are the same, so that's why we have 1 over 1 over here, and we got 50,000, so it means 50 kilobaud, right? Okay. So actual bandwidth of a digital signal is infinite. So when we talk about a signal, so let me draw a signal over here, right? So if we have a digital signal like this, so it will be having infinite bandwidth, right? But remember, the effective bandwidth is finite, right? So this is, we have to be very, very careful that if we talk about the Fourier, right? So there are a lot of different components within this signal, but there are some components that are effective, right? So that's why we ignore the rest of the components. We take the components which are actually taking, or which are actually contributing the maximum power within that signal, right? So we ignore the other frequency components. Bandwidth is proportional to the signal rate, baud rate. The minimum bandwidth can be obtained by C into R into 1 over R, right? And now we can have the N maximum, right? Data rate if the bandwidth of the channel is given, right? So we can find N maximum 1 over C B into R, right? So just little mathematics over here. So here are some of the terminology when we talk about the data communication. Baseline wandering, decoding our digital signal. The receiver calculates a running average of the received signal power. The average is called the baseline, right? The incoming signal power is evaluated against this baseline in order to find the value of the data element. So if we have a long string of zeros, or maybe we can have long string of ones, so it can cause a drift in the baseline, right? So that is something about the baseline wandering, and as a result it is difficult for the receiver. So the problem actually is at the receiver side, because we don't have any problem to transmit a string of zeros or a string of ones. So the actual problem is at the receiver side. So when it has to decode this long string of zeros and long string of ones, right? So there can be a drift in the baseline, right? So we can have a shift up or maybe a shift down. So the receiver is actually wondering to find out the baseline. So a good line encoding scheme needs to prevent baseline. So it has to preserve the baseline. There should be maybe synchronization between transmitter and receiver in order to fix the baseline. And then DC components, that is also important part in some scenarios of the signal. Voltage level in a digital signal is constant for a while, for a certain amount of time, creates very low frequencies, right? Those frequencies, they actually are very close to the zero, right? Around zero, and they are actually called DC components, and they present, actually they are the main reason for problems for a system that cannot pass low frequencies, right? So if we have to suppress low frequencies, so those DC components will be stopped there, right? Or the system that uses electrical coupling via the transformer, telephone line cannot pass frequencies below 200 Hertz. A long distance link may use one or more transformers, right, to isolate different parts of the line electrically. So here we have the problem with the DC component, right, scheme. So there should be a reasonable scheme, right, so that we can avoid DC component if we can. And then self-synchronization, that is another important element. In order to interpret the signals received correctly, right, from the transmitter, bit interval must correspond exactly to the sender bit interval, right? So there should be some start and stop. Receiver clock is faster, right? So this is all about the synchronization. Or slower, the bit interval are not matched and the receiver might misinterpret the signal, right? So there should be a synchronized between the sender and the receiver, start bit and stop bit, right? So here we are going to show the lack of synchronization between the sender and the receiver. So you can see that this is the sender in A, and on B we have the receiver, right? So this is the dotted lines are showing the start of next bit, and here we have the stop of this 0, and then we are going to start 1, right? So you can see that we have clear line mentioning the start and the stop of the bits, right? So if the clock at the sender side is not properly synchronized with the receiver side, right, so then you can see the problem, right? So 1, it will take this as 1, and here we have 0, 1, 1, 1. So if you look at the data only, right, so 1, 0, 1, 1, 0, 0, 1, so you can see that how the receiver is interpreting this data, because they don't have proper synchronization. 1, 1, so again error, 0 and 3 ones over here, we have 2 ones over there at the sender side, and then 0, 0, 3 zeros, and you can count the number of zeros, right? So again here we have 2 ones, right? So a self-synchronizing digital signal includes timing information in the data being transmitted, so we can also include the timing information. See if there are transitions in the signal that alert the receiver to the beginning, middle, and the end of the bit, right? So start bit, stop bit, or maybe the mid of the. If the receiver's clock is out of synchronization, these points can reset the clock. So we can reset the clock and resend the and take some corrective actions accordingly. So here we have another example. Receiver clock is faster than the sender clock. How many extra bits per second does the receiver receive if the data rate is 1 kilobit per second? How many if the data rate is 1 megabit per second? So we have two different data speeds, and the clock is 1% faster than the sender clock. 1 kilobit, if we have the data rate 1 kilobit per second, the receiver receives 1001 bits per second instead of 1000, right? And send, and these are the receive bits 1001, one extra bit per second. So if we have higher data rate 1 megabit per second, receiver receives 1001,000 bit per second instead of this, right? So this is sent, and on the receiver side you can see we have errors, right? So 100, this one is the extra bits per second. Okay, so before starting the actual encoding, right, so we need to go through certain terminology. So we should be able to understand unipolar, polar, data rate, right, duration and length of a bit, modulation rate, right, and mark and space. So all signal elements have the same sign, right? So no polarity, single polarity, unipolarity, so they have the same sign, right? And in polar, one logic state represented by positive voltage and the other by negative voltage. So here we have the polarities, right? So here we have same sign, right? If we are using positive, we will be using positive all the way, and if we are using negative, we will be using negatives. But here we have to perform transitions, right? One logic state will be going to represent by the positive voltage, and the other will be by using the negative. And then the data rate, right? So this is very important term. Transmission in bits per second, and duration or length of a bit, time taken for transmitter to emit one bit, right? So when we talk about the data transmission, so each bit has a amount of time, so time taken for the transmitter to emit one. Rate at which the signal level changes, right, and it's measured in baud, mark and space. So binary 1 and 0, 1 is mark and space is binary 0. So let's start the encoding techniques. So first of all, we are going to start unipolar. So over here you can see it uses only one signal level, one polarity. So you can see in this this is the you can say the crossing 0 level, and you can see that we are going to use only one signal level. So we can use another if we have to use negative, so we can also do that. High voltage is binary 1, no voltage is binary 0. So it means if we are 0 at this level, so it means 0, and high voltage is 1, so that should be synchronized, and that should be there should be understanding between sender and receiver when we are going to use this sort of representation or encoding. Easy to implement, right? So we need very simple circuitry, not self-synchronized. You need a very hi-fi sort of synchronization, has a DC component, right? So we talked about the DC component and the problems we can come across and we have to face when we talk about the DC component. Polar counterpart. This scheme is very costly, right? The normalized power, right, that is the power needed to send 1 bit per unit line resistance, is doubled that for the polar non-return to 0. This scheme is normally not used in data communication, right? So this is, but we have to go through this because this is a very basic scheme, right? So you can see here we have the data 0, 1, 0, 0 and 1, 1, 1, 0. And you can see 0 is no voltage and 1 is we have the voltage, right? So absence of voltage is marked as 0, and the presence of voltage for a predefined time span, and then 1, 1 and 0. Okay, so here we have different types of polar encoding, right? Positive and negative polarity. So you can see that we have in polar, if we want to classify polar, so we have non-return to 0, return to 0 and biphase, right? And when we talk about non-return to 0, so it's non-return 0L and non-return 0 inverted. In biphase we have two more classifications, Manchester and differential Manchester. Okay, so here we have non-return to 0 encoding scheme, can be of two types, right, as mentioned. And if we go back, so we have two different types of non-return to 0, L and I, right? Level 0 is encoded with one polarity, say 5 volt, and 1 is encoded with another polarity, say minus 5 volt. That is non-return 0 level L, non-return 0 inverted. So 0 is encoded with no change in polarity from previous bit, 1 is encoded with change in polarity from previous bit. So better synchronization with NRZL if one's bits exist in data stream, right? So if we have long stream of 1, so then NRZI gives better performance as opposed to NRZL. Zeros can still cause synchronization problem when we talk about NRZL or NRZI, right? So here we will be talking about NRZL and NRZ inverted encoding scheme. So you can see 0 is represented by positive 5 volt, right? So if this is the 5 volt, let me write down over here. So here we have plus 5 volt and here we have minus 5 volt. These are the levels. So plus 5 volt is 0 and minus 5 volt is 1. Plus 5 volt 0, 0, right? And if we talk about the inversion, so you can see the transition between the next bit is 1, right? So 0 plus 5 volt and this is 1, 0, 0, right? And here we have to represent, so here you can see that 1 is represented by negative 5 volt and next time 1 is represented by using inversion, right? So here 1 is represented by minus 5 volt and next time keeping in mind, right? So you can this is very, very important that we need memory over here, right? So we need to remember that the previous one was represented by minus 5 volt and the next one has to be represented by plus 5 volt, right? So again we need memory over here, right? So we need to remember that previous one is encoded by plus 5 and the next one is going to encode by minus 5, right? So this is all about inversion. Transition between next bit is 1, right? So it means we need memory over here. We need to remember. So here are some of the advantages and disadvantages of NRZ, right? So it should be NRZ. So there's a mistake, so NRZ, right? Easy to engineer, so we have because they are simple and we can even go for the circuit design, right? So it's very easy and we have to use simple components in order to apply this encoding and decoding, right? And we can use the bandwidth effectively and efficiently. And here are some of the disadvantages, right? So DC component, as mentioned earlier, that there are some problems if we have a low pass filter because the DC components, they has to be near 0, so those will be suppressed. Lack of synchronization, right? So we talk about the synchronization problem over here. And here are some of the usages, for example, use for magnetic recording, right? So they are not used nowadays by most of the systems. And then we have return to 0 encoding, has poor synchronization performance, and this inversion has better synchronization for stream of ones, but it has to face certain problems when we have continuous stream of zeros, right? So return to 0 encoding overcomes this synchronization issue by using 3 voltage levels, right? Positive, negative, and 0. Before we are using only 2 levels, plus voltage, minus voltage, right? Or maybe in unipolar we are using only 1 level. So over here we are using 3 levels, right? The circuitry or the implementation will be bit more complex over here. 1 is encoded as plus V, right? And 0 is encoded as minus V transition, right? So this is, you can say, the falling edge plus V to 0V, right? And this is the rising edge, right? Efficient than NRZ because it has more transition, right? So higher frequency component, right? So here we have return to 0 encoding, right? So 0, right? And then you can see that the transition at the middle of the bit 1, and next we have the 0, right? Again 0, right? And here we have to represent 1, right? 1 and 1. So you can see in the middle of the bit we have to touch the reference line, right? So it can be used for synchronizations, right? So these transitions in the middle of the bit, they can be effective for synchronization. So here are again different types, because we have only return to 0, and now we'll be talking about the biphase, right? Manchester encoding, polarity inversion in the middle of each bit period, right? Low to high represents 1, high to low represents 0 for bit representation as well as synchronization purposes, right? So Manchester achieves the same level of synchronization as return to 0 with 2 voltage levels. So here we are using 3 voltage levels, right? So higher voltage, and this is the 0, and then negative voltage. 3 levels has to be used over here, but in Manchester we are using only 2 voltage level. So let's talk about differential Manchester. In the middle of the each bit period, right, is used for synchronization only, right? So here we have the some additional mechanism, that is transition in the middle of each bit. Start of a bit period represents 0, no transition at the start of a bit period represents 1. So it requires 2 signal changes to represent 0 and 1 signal change to represent 1. So we need 2 changes to represent 0, and so here we have Manchester and differential Manchester. 0, right? So you can see 0, right? And then this is 1. So this is you can say falling, and this is rising, and you can see the transition in the middle of the bit, right? So again 0, right? And here we have the 1 again, because we need this, right, in order to represent 1, and then again 1, and this is 0, right? This is 0. If we talk about the differential Manchester, so you can see presence of transition at the beginning of the bit time means 0, right? So this is 0, right? And then 1, 0, right? Again 0, right? So you can see the presence of transition at the beginning of the bit, right? So this is transition at the beginning, right? So if we have the transition and if we go back, right? Okay, so it means for 0 we have 2 transitions, and for 1 we have only 1 transition, right? So this is 1. So again 1, right? 1 and 0, you can see 2 transitions. So again changes to represent 0 and 1 signal change to represent 1, right? So let's talk about the comparison, Manchester versus differential Manchester, and those encoding schemes, they lie in the category of biphase, right? So encoding rely on signal transitions to encode data. So we have to look for the transitions. Both have better performance in the presence of noise, right? So because due to a lot of transitions, so it has more immunity to noise. Any encoding scheme that relies on absolute voltage level to encode data. Easy to lose sense of the polarity of a signal in a complex transmission layout, right? So we can lose the sense of polarity. So here are some of the biphase pros and cons, right? So per bit time and possibly 2. So this is the journal, right? So if we talk about biphase, right? So irrespective of Manchester or differential Manchester, per bit time and possibly 2, right? This is about differential Manchester. Maximum modulation rate is twice, right? So we need more baud rate, more bandwidth. So as a result, we need more bandwidth. So here are some of the cons. Synchronization on middle of the bit transition. So self-clocking. So there are no DC components. So we mentioned the problem with DC components, and we can detect errors as well as opposed to other encoding schemes. Okay. So then we have alternate mark inversion. Mark mean 1, right? And AM means alternate, right? 1 inversion. Voltage polarity for successive 1 bits. 0 bit will be represented by 0 volt, right? Self-synchronization. So there is again a problem of for long stream of zeros. It has no DC components. So here we have bipolar AMI coding example. So you can see 0, this is 1, and the next one is, right, has the opposite polarity. So again memory is required. We need to remember that previous one was encoded by using plus, and now we are going to use negative. So next one is again, right, by positive voltage, and next one, so we need to remember previous one is represented by plus and the next one is represented by, right? So again, so here we have some sort of comparison between AMI and pseudo ternary. So you can see here, if in AMI 1 is represented by this voltage level, so next one will be represented by the inversion of this voltage. So this is plus and this is negative. So if we talk about the pseudo ternary, so you can see over here that we are focusing on zeros. So the absence of voltage mean 1 and the presence of voltage is represented by 0. So over here you can see if this 0 is represented by positive voltage, so the next 0 has to be represented by negative voltage, right? So and you can see this 0 negative and the next 0 is represented by positive voltage. So inversion again, so the absence of voltage is 1 and again this 0 was represented by positive voltage, and here we are using negative voltage in order to represent the next 0, right? So here this is something you can say we are focusing on 1 and the 0 is encoded as the absence of voltage, and 1 is taken as the presence of voltage, but we have to invert the voltages on successive ones, right? On, for example, if we have a 1 here and this is a sort of successive one, if we ignore those zeros, so this voltage is plus and this is the negative. So we are doing the same but on zeros over here, and we are using different or opposite sort of representation. 1 is absence of voltage over here and 0 is the presence of voltage but with inversion. So here we have multi-level representation. So the name is, tag is 2B1Q. So we are going to represent 2 bits with 1 by using 1 signal. 2 binary, 1 quaternary uses data pattern of size 2 and encode the 2-bit pattern as 1 signal. So we are going to use 1 signal, right? So this is the transition table. Next bits 0 0, starting from 0 0, 0 1, 1 0, 1 1. Next level, right, and next level. Previous level positive and previous level negative. If we start from 0 0, this is represented by plus 1, right? So this is plus 1 and 1 1. Then we have to go for the minus 3, and here you can see we have 0 1, right? So 0 1, you can see next level, right? If the previous level, our previous level is minus 3, then our next level is again will retain as minus 3, and then 1 0, so minus 1, and next level for 1 0 is plus 1. So that's why we have a plus 1 over here, and then 0, 1, right? So again we have plus 3. Send data 2 times faster because we are sending 2 bits, right? So in one signal, so this is one signal and we're sending 2 bits, right? As opposed to NRZ level, however, uses 4 different signal levels, which means the receiver has to decide among the 4 different levels, right? So receiver, the decoding side has to work a lot. So here we have another multi-level encoding scheme that is 8 bits, 6 ternary, right? So we are going to encode a pattern of 8 bits as a pattern of 6 signal elements, has 3 levels, right? So ternary, so that's why we have a T over here. So we cannot show the transition table as we showed over here because there we have a huge number of entries over here. So you can imagine have 256 different data patterns and signal patterns, right? So we are not going into details as a result. So we have 4D PAM, 4-dimensional 4-level pulse amplitude modulation. Data is sent over 4 lines, right? As at the same time uses 5 voltage levels such as -2, -1, 0, 1 and 2. Level 0 is used only for forward error correction. So this reference is used only for forward error correction to send data over 4 channels, right? So you can see it's a sort of demultiplexing looks like, right? So these are the bits, right? And you can see we have different capacities, wire 1, right? And then wire 2, wire 3 and wire 4, and different links they are having the capacities, and this is what we have to encode, right? And then we have MLT 3 scheme. So if the next bit is 0, there is no transition, right? So you can see if the next bit is 0, there is no transition, right? So 1, next bit is 1, the current level is not 0, right? And the next level is 0, next bit is 1 and the current level is 0. So you can go through the rules, right? So next bit is 0, so no change, right? So same as NRZ I inverted with greater complexity. So here we have to accommodate more rules, right? More values. So here we have the summary of the line encoding scheme. So category, this is the name of the scheme and the bandwidth average, and the characteristics the underlying scheme is providing. If we talk about the unipolar, it's we have non-return to 0, and the average bandwidth is n/2, costly, and the cons are no self-synchronization. We have a long string of zeros and ones, and we have a DC component, so we have problems. Then we talk about the unipolar category. So here we have 3 different types of schemes: NRZ level, NRZ inverted, biphase, right? So bandwidth is n/2, no self-synchronization again if long zeros and ones, so same problem with NRZ. And here we have NRZ I, right? No self-synchronization for long zeros, right? So it can accommodate a long string of ones, right, as opposed to NRZ L. And again we have the problem with the DC component. And then biphase, right? So here we have the bandwidth is equal to n, right? So improvement, self-synchronization, right? So no DC component, high bandwidth. So you can see we have accommodated a lot of problems by using biphase. And if we talk about the bipolar, right, AMI, bandwidth is again n/2, no self-synchronization for long zeros, and we again have the problem with DC component. 2B1Q, bandwidth is reduced, right? Self-synchronization, no self-synchronization for long same double bits. And if we talk about B60 8 bits, 6 signaling levels, and multi-level. Over here we are talking about the category multi-level, right? So if I go back, 8B6C, right? So that is here. So 3 levels are used, right? So here you can see the bandwidth self-synchronization is available over here between transmitter and receiver, and it also have no DC component. We talk about 4D PAM5. Bandwidth is on the lower side. It provides or supports self-synchronization, and we don't have any DC component. So MLT 3, and bandwidth is again lower side, on the lower side, and no self-synchronization for long string of zeros. So if we talk about the digital to digital conversion, so we have to take into account 3 different techniques, right? So line coding that we talked about, block coding, and scrambling. So let's talk about the block codes, right? It ensures the synchronization, and it provide error detection, right? So we can detect errors by using block coding. So one thing has to be mentioned over here, that this is a must for us, right? When we talk about the communication, so line encoding has to be there, because we have to make our data compatible with the underlying channel. So in order to do that, we have to perform the line encoding, right? Signaling, proper signaling technique. And those are the choices. So in some cases, some scenarios, we are going to use block codes and scramblers, and in other scenarios we can avoid them. So there are advantages, but the cost is our circuitry, our communication system will be more complex. So they ensure synchronization, and they provide, we can detect errors, right? And as a result, the performance is improved, right? Block coding changes a block of m bits into a block of n bits, where n is larger than m. So of course, because we are going to add some redundant bits, so that is for sure that n bits will be larger than m. Refer to as mb over nb, where n is larger than m. So here are the example, right? So stream, we actually divide a stream of bits into m bit groups, right? So m bits, and then mb to nb substitution. So we replace them after encoding those blocks, right? So n bits are greater than, because we are adding redundant bits. So 3 steps. First of all, division into blocks. Sequence of bits is divided into groups, so we have to perform the division. 4B, 5B encoding, the original bit sequence is divided into 4-bit groups, and then we have to substitute. We substitute an m-bit group of an n-bit group, right? For example, 4B, 5B encoding, we substitute a 4-bit code for a 5-bit group, right? Then we have to concatenate, combination, are combined together to form a stream, right? So bit stream. So here are some of the codes, 4B, 5B, right? So this is the data sequence or block. This is the encoded sequence, and we can have so here control sequence and encoding sequence. So here you can see 4B, 5B. You can see 4 bits, right? And these are the 4-bit blocks, and these are the corresponding 5 bits after encoding, right? So 4 ones, so you can see we have this encoding. We talk about 001, right? So you can see 3 zeros, they are scrambled over here. Okay, so now we are going to use AMI for scrambling, right? So bipolar AMI encoding has a narrow bandwidth and does not create a DC component. So that is, we all know, we have just discussed that. long sequence of zeros, so there is a problem, upset the synchronization. So what we can do, we can scramble this long string, right? And if we can find a way to avoid a long sequence of 1, so that is the scrambling we are going to use. Can use bipolar AMI for long distances, right? So to provide synchronization, not increasing the number of bits, solution is to substitute long zero level pulses with a combination of other level to provide synchronization, and that is actually scrambling. Block coding is done at the same time, so we have to accommodate scrambling whenever we are encoding, right? So this is opposite of the block code. So a system needs to insert the required pulses based on the defined scrambling rules, right? So we have to define scrambling rules. So here we have the example. We are required to send data at this data rate 1 megabit per second. What is the minimum required bandwidth using a combination of 4B, 5B, and NRZ-I or Manchester coding, right? So increases the bit rate, right? So of course we are adding extra bits, right? So we have more, we need more data rate, right? So the minimum bandwidth using NRZ is n by 2, so 625. So if I divide this by, right, so n by 2, and then the Manchester scheme needs a minimum bandwidth of 1.25 megahertz, lower bandwidth but has a DC component problem, right? This first choice, right, that is NRZ-I. Second choice, right, needs a higher bandwidth, does not have a DC component. So there is a trade-off all the time, right? So here we have no DC component, but we need more bandwidth, right? So here we have a DC component problem, right? And so there is a trade-off all the way. So 8B, 10B block encoding. So 8-bit, and we have divided 5-bit 6B encoding and 3B, 4B encoding, and here is the controller. Okay. So as a result, of course, when we are going to add more redundant bits for error detection, and maybe some of the encoding schemes, they may support error correction as well. So add more redundant bits and can thereby choose code words that would prevent a long run of voltage level, right? That would cause DC component. So as far as the scrambling is concerned, so here are some of the key points. Code is one that does not increase the bandwidth for synchronization, and it should not have the DC component. Used to create a sequence of bits that has the required C/C for the transmission, self-clocking, no low frequencies, no wide bandwidth, right? At the same time, so this we know it replaces unfriendly runs of bits, for example, long string of zeros, long string of ones, with a violation code that is easy to recognize and removes the unfriendly. So here we have two different types of B8 ZS scrambling, right? So here we are going to represent long string of zeros with this one, and in here you can see we are going to represent the long string of zeros with another code 000V and then B0V 00V, right? So here are two different choices, right? So you can see this one we are going to represent long string of binary zeros, 8 zeros with 00V, B0VB, right? So 00V, B0VB, VB. HDB3 scrambling technique. So here we can have different situations over here. So here we have zeros, right? And so you can see B00V, and here we have 00V, right? And here we have again even, right? So first substitution, and this is the second. Here we are even, odd, even, even, right? Okay, so that is again the same. Okay, so that's all for today's lecture. So today we talked about encoding schemes. So data representation, we have to deal with analog and digital data as well. So our system should be capable of storing, retrieving, and maybe accessing the data that is available digitally or analog data. So we need to represent data effectively and efficiently for its storage, for its retrieval, for its transmission from one point to another point. Then we talked about the data transmission. So we need to, after the data representation, we need to send that data from one point to another point. So for that we need signaling. So we have a lot of different choices. We can use analog signaling as well as digital signaling, irrespective of the type of the data. So in today's lecture we were focusing mainly on when we have digital data and we have to use digital encoding. So we talked about different encoding techniques, and there are different encoding schemes that we can use when we have to deal with digital data and digital encoding signaling, right? And we talked about the advantages and disadvantages of the digital transmission, and then we talked about the bit rate and baud rate that are very important parameters when we talk about the data transmission. Then we have different types of talked about different types of encoding schemes. We discuss unipolar, polar, biphase encoding, right? And then bipolar encoding, and then we also talked about different choices, line encoding and block codes, and then the scrambling. So line coding is a must, and the other two ones, they can be used accordingly, right? So for example, when we have long string of zeros, so we don't have a very efficient encoding scheme in our system, so we can deploy the scrambling in order to scramble those long string of zeros and long string of ones, right? So and then we talked about different block codes also, and different scrambling and block coding mechanisms. So that's all for today's lecture. अपना ख्याल रखिएगा. मेरी तरफ से अल्लाह हाफ़िज़. अस्सलाम वालेकुम.